right? We have a point load. And so this will be equal to 0. Okay. So we have V at point A, which is also equal to the shear force at distance x is equal to 0. Okay, so this one I will say V, right? V, the distance is equal to 0, right? And this will be equal to omega L minus 2A divided by 2, right? Because we have found that, right? We have found the reaction force, right? So AY is equal to omega L minus 2A divided by 2, or bracket L minus 2A divided by 2. So that is your shear force at point A. And over here, what we have determined at point A is not a function. This is a constant. Okay, this is a constant, right? So moment at point A, right? And this will be equal to moment at a distance 0, and is equal to 0, right? Why? Because this expression over here, dv over dx equal to, so v as a function of x down here, right? You cannot use this expression over here. You cannot say, okay, Eugene, so once we know v as a function of x, we integrate, right, 0, right, dx, and this is moment about x. Yes, sorry, this is dm by d. In fact, you can also use this relationship. Okay. So m as a function of x is also equal to 0. So I have a fixed point, moment at point 0 is equal to 0. Okay. So this can be equal to 0. Okay. So for this case, you found your V as your shear force equation, or for this case, is a single point is omega L minus 2A divided by 2, and M as a function of x is equal to 0. So all this over here, right? So this thing over here, they are all a what? Constant. They are not a function of x. Okay. Right. Now let's look at between point A to point B. Okay, let's look at between point A to point B. Right. So we are going to focus on point A. I will divide the page into two. Okay, so now we are going to do between. So the diagram is on the side, which is good. So now we are going to do between point A to point B and 0x to A. So what we're going to develop now is a function. It's not a constant like before, because it's ranging from point A to point what? To point B, okay? So we still know, what we still know is dV by dx is equal to minus omega as a function of x. There is no distributed load, right? So this is still equal to what? 0, right? So when you write over this side, so you have V as a function of x minus by V at point A. So this will be equal to 0 to x, right? And you integrate 0 dx. So this will become what? So V as a function of x minus VA, you know VA is omega L minus 2A divided by 2. And this will be equal to what? 0. So now we have V as a function of x is equal to omega L minus 2A divided by 2. Okay. And this will be equal to what? This will be equal to dm by dx. So over here, this is a equation. It's no more constant. Okay. This is an equation. So I'm going to call this equation number 1. Then the next thing that we do when we integrate, we have m moment. Now we're going to integrate. So moment as a function of x minus by moment at point A. This will be equal to, so this will be 0 to a distant x. Now you have what? Omega L minus 2A divided by 2 dx. Okay. So m as a function of x, we know that moment at point A is equal to 0. So this will be equal to omega L minus 2A divided by 2x. Okay. So this is your equation number 2. Right. So still no distributed load. Right. So this method is still possible to use when you have non-distributed load. Okay, when you have non-distributed load, you can still use the same, you can still use the same equation, okay, or same approach. So now immediately you write down here, this is equal to omega L minus 2A divided by 2. Whereas m as a function of x will become what? Will become omega L minus 2A divided by 2 multiplied by what? X. Okay. Then we do the next point. I'll show 2 more points, then I'll stop. Okay. So now we look at point B when x is equal to a now. Okay. So all you need to do is you just apply or use or substitute x into equation 1. So because x is equal to a now, what we are finding now are what? Constants. Okay. So the shear force at point B is equal to, so you look at equation number 1, is still, so if you look at equation number 1, is still equal to omega L minus 2A divided by 2. Okay. And then for the moment, when you substitute x into equation number 2 now, right? So moment at point B, right? So if you look at equation number 2, now you replace x with a. This is omega L minus 2A divided by 2 multiplied by a. Okay. So we can write down. So that is our exact value at point B. Okay. So over here, you still have omega L minus 2A divided by 2. And this is equal to L omega L minus 2A divided by 2, and you have A. Now this over here is a what? Constant. Because your x is not varying. Your x is A, the one before x is equal to 0. Now let's look between point B and point C. Is where things get interesting. So okay. So now we're going to look at between point B to point C. And now it's A, X, and L minus A. Okay. So now what we have now, okay, let me get the same diagram if I can copy. Right? And then I'll paste down here. Right. So what you can see now, between point B to point C, you have a distributed load now. Okay, you have a distributed. So now all you need to do now is just say dV by dx. Between point B to point C, you know that you're going to have what? Minus omega as a function of x, or just minus omega, right? So you're going to write down V. So the limit is V as a function of x minus by the shear force at point where? At point B. So this will be in the limits of A to X, okay? And then you know that this has to be minus omega dx, okay? So from here, you know that V as a function of X, so minus VB, so we know what is our VB, right? Omega L minus 2A, right? Divided by 2. So then over here is equal to minus omega X, and is bounded by A and X. Okay, so you have over here V as a function of X will be equal to minus omega X minus by minus omega A plus by omega L minus 2A divided by 2. Okay, so we simplify things. So minus omega X plus by omega A plus by omega L over 2 minus by omega A. So you can get rid of this. So what we have is equal to minus omega x plus by omega L divided by 2. So this will be equal to your dm by what? dx. Okay, so this is my equation number 3. So immediately you go to your table, you can write this down as minus omega x plus by omega L divided by 2. Okay, so then we integrate, right? So again, this will be m as a function of x minus m at point B, right? At point B, which we have identified what's a moment of point B. Now we're going to integrate from A to x minus omega x plus by omega L over 2. This thing will be dx. Okay, so mx, m as a function of x, and then this will be minus omega L minus 2a over 2 multiplied by a. So this will be equal to minus omega x squared divided by 2 plus by omega Lx divided by 2. The limits is x and a. Okay, so you have m as a function of x minus omega L minus 2a divided by 2a. So this will be equal to minus omega x squared over 2 plus by omega Lx over 2 minus by minus omega a squared over 2 plus by omega La over 2, close bracket. So I'm not going to waste your time. Finally, when you simplify this, okay, remove all the bracket, you have m as a function of x is equal to omega over 2 minus x squared plus by Lx minus by a squared. So you have over here, right, this will be equal to omega over 2 minus x squared plus by Lx minus by a squared. Okay, so the procedure repeats itself. Okay, so what I've just shown you is this. Okay, two things you have to know is that you can also apply the integration method, okay, for point load combined with distributed or just with point load. You can do that. Okay, but if you just have point load, I will just use positive shear, positive bending moment. Okay, if your load, this is just to explain I'm just trying to teach you, to show you how does integration method work for point load. And then the next important thing that you have to know is whatever point that you want to find now, you need to know what's going on before. Okay, like over here, in order to find between B to C, I need to know what is going on at VB, right? I need to know what is going on VB. We need to know what is going on from moment about point B, moment about point B. That is the most important thing. Okay, so with that, I'm going to stop the lecture now. Do not go yet. Okay, I'm going to stop recording.